Okay, so for this one, percent composition of compounds. This is the worksheet. We're just gonna work through this. So for this one, it's for number one, it says define a compound, right? So from the first thing, a compound from our first worksheet. A compound is a pure substance composed of one or two or more, sorry, two or more types of atoms bonded together. So we have two or more different types of atoms that are bonded together. This forms a compound. Um, Next, it says, based on the drawings below, identify which drawings are compounds and which are elements. So from our first worksheet, right, we said elements are pure, right? They're either atoms, right, just by themselves. That's an element, right, just hanging around by itself, or an atom bonded to the same type of atom. So oxygen bonded with itself, or there's a whole bunch of others, right? So two, um, this one is an element, right? I'm going to be a little more specific here. This is an element, but specifically these are atoms, right? Individual atoms, but these are elements, right? This is also an element, right? It is pure, it is by itself. There are no other colors, there's no other types of atoms, there's just one. Now, this is called a molecule from our definitions from the first worksheet. Lastly, we have compounds, right? Where there's two or more different types of atoms, right? We can clearly see here that there's a red and a green bond, that those aren't the same. So I don't know if it's a molecular compound or ionic, because I don't know if it's a metal or non-metal. All right, so next we're going to define what a chemical formula is. So a chemical formula is a way that we can represent a substance with uh, their elemental symbols and numbers. So we say and define it as a symbolic way to represent substance composition. Oops. Just like that. So the chemical formula of a compound with one carbon and two oxygen atoms, CO2. Where does this come from? Right, so there's a kind of a one here that we don't draw in. If it's one, you don't put it in, right? You can draw it in if it helps you with reaction problems, but we don't draw the ones in. So CO2, right? There's one carbon atom and two oxygen atoms. So these subscripts go right next to whatever they're kind of describing, right? The two oxygens or the one carbon. This doesn't mean that there's two CO2 COs, right? This is CO2 versus this is two COs. So just be careful, right? This is CO2, goes with the thing right next to it, the subscript to its left. 5, true or false? It says different compositions of the same atoms create different compounds. This is true, right? You can arrange atoms in different ways, have more or less of a certain atom, and this will give you different compounds, very, very different compounds. So you'll see more of that later. Fe2O3 and Fe3O4 are the same and have similar properties. This is not true. As I just said, right? If you change the ratio of things to one another, you get different properties. Right? This has two irons and three oxygens. This has three irons and four oxygens. The atoms, the types of atoms are the same, but they're not in the same ratio to one another. And also, um, the charge of iron is different. So they're not the same. The atomic ratio of Fe2O3 is 2 to 3 iron to oxygen, right? That's true. There's 2 irons and there's 3 oxygens, so 2 to 3 ratio. D, it says iron makes up 40% and oxygen makes 60% up Fe2O3. This is false. So this percent doesn't account for the mass of each atom, right? Iron weighs, if you look at your periodic table, look at that mass number from that last worksheet, iron weighs significantly more than oxygen. Oxygen is 16. I think iron is about 58.4. And so iron makes up more than 40%. If you're talking about number of atoms percent-wise, right, it does make up 40% of the atoms in Fe2O3, but it does not make up 40% of the mass, which is most commonly what we refer to. Next, it says the molar mass of an atom must be considered when calculating the percent composition of a compound. This is true. Right? We usually don't talk in percent atoms. We usually talk about percent composition, right, by mass. Last one, it says Fe and O have the same contribution to the total mass. Fe3O4. So they're, again, they don't, if you add them up, iron weighs a lot more in total. So you can do the math, right? Add them up on your periodic table. The oxygens add up to 64 and the iron is going to be like 100, like 18 about, or 17 or something. Okay, that is it for 5. So what are the units of molar mass? The units of molar mass are in grams per mole. The reason we call it molar mass is how much mass do you have per 1 mole, right? So I have 30 grams per 1 mole of something, right? That's the units of molar mass. So grams per mole, how many grams per 1 mole? Define the units of molar mass using, so define it. So I kind of just said it, right? It's the mass of substance per 1 mole of substance. That's how we define this. All right, number 8 says calculate the mass of each element or compound below using the units of molar mass. So you look at your periodic table and we basically just add them up, right? So O2, we clearly have 2 oxygens, right, from this subscript. So we have 2 oxygens. Each weighs, I'm going to round to make this easier. Each weighs 16. So 2 times 16. And then this is 32 grams per mole, right? The 16 is in units of grams per mole. Now, if we're talking about 1 mole of this, we'll kind of define what a mole is later when we use Avogadro's number. But a mole refers to a certain number of things, kind of like a dozen of eggs. Mole refers to 6.022 times 10 to the 23rd of something, which is Avogadro's number, which we'll see later on. So for 1 mole, we have 32 grams. Now I am just going to pretend like all of these are in 1 mole from now on, just so I don't have to do that second step. So for CO2, right, you can figure out the grams per mole. So carbon is 12. We just did O2, that is 32. And we end up getting 44 grams for 1 mole of CO2. Remember, I'm doing this for 1 mole. Right? You can multiply this by 1 mole, and the units will cancel out. Just to show you, this is grams of O2. This is for the first one, just in case anyone wants to see it. So this cancels out, right? We're left with 32 grams of O2. For the iron, right, it's very similar. So the iron, we have 55, sorry, 0.85. We have 3 of them, and then we have 4 oxygen, so 4 times 16. This gives us 231.55 grams of Fe3O4. And so, again, for 1 mole of Fe3O4, this is how much it weighs. H2O, 2 plus 16, this is 18 grams for 1 mole. Remember, doing this for 1 mole. 2 moles will weigh different. All right. Now, practice. It says calculate the percent composition of FeNO and Fe2O3. So we're given a formula all the way up here. It says the total mass of atom divided by the total mass of compound times 100% is equal to percent composition of an atom. So what we're going to do is first find the mass of both of these, and then, or specifically the mass of iron in this, and then we're going to divide it by the total mass. So the mass of Fe2, right, is just 55.85 times 2, right? I thought it was 58. I think I need a better periodic table. It's a little worn out. That's 55.85. So this ends up weighing, what, 111 or something. 111.7 grams per mole if you want to keep the units. Next is the mass of Fe2O3. So this is 55.85 times 2. This is from the iron. And I forgot to put my units of grams per mole here. Plus 3 times 16, right? And this is from the oxygen. All right, so I add this all up. And we just add 48. And we get 159.7 grams per mole. So now all we have to do is to find iron is 111.7 divided by 159.7, right? You can keep the grams per mole. They end up canceling out. And then we multiply this by 100%, right? With any percent, you divide something by something else and you multiply it by 100%, right? So you have 20 tomatoes out of 100 fruits, 20 divided by 100 times 100%. That's 20% tomatoes. So we go ahead and divide this. And we get 69.94% iron, right? Because the iron is on top. So comparing iron to this whole thing. So this is 69.94% iron. And then oxygen, we can do the same thing, except I'm going to make it easier, right? There's only iron and oxygen. So you can just do 100 minus 69.94. Right? These are both in percents, right? Percents are out of 100. So you do 100 minus that and you end up getting, oops, wait. End up getting 30.06% oxygen. And that's it. So for the percent composition in carbon and oxygen CO2, I'm just going to do the same thing. This one will be a little bit faster. So carbon is 12 grams per mole. We only have one. For the oxygen, this is going to be, we have two oxygens, right? So this is 32 grams per mole, 16 plus 16. The percent composition of carbon, I'm going to do 12 grams per mole divided by 32 grams per mole times 100%. Oops, I forgot to add them. So my apologies. It should be 12 plus 32, right, which is 44, as we did on, I think, the above for doing CO2. So 12 divided by 44 times 100%. And we get 27.27%. Now, to do the same thing for oxygen, 32 divided by 44, I'm just going to do 100 minus 27. So 72.72. This is percent oxygen. Oops, sorry, 73. And that's it for 10. Last one, it says calculate the percent composition of NaHC and O in this. So for just to kind of start this off, we have to find the mass of each. So the mass of Na, let me check. I think it's 23. Yeah, it's 23 grams per mole. Hydrogen is 1 gram per mole. I have one carbon, which is 12 grams per mole. And I have 3 oxygens, which is 48 grams per mole. Right, 16 times 3. And I'm rounding. So just to make the math easier. I add these all up. And I'm going to get some number. Being 84. And now I have to just do all of these. So 23 over 84. I'm not going to write the grams per mole, so I don't have to write them all in. Times 100%. I don't want to have to do this 4 times over and over. That's why I'm just excluding it, right? They cancel out. So the sodium percent, right? Sodium is the 23, where that came from. This is 27.38%. Down here, we have 1 over 84 for hydrogen. This is 1.19%. Let me label these. That's hydrogen. Carbon, again, is very similar. Just dividing and multiplying by 100. This is 1 point, it's not 1, 14.29% carbon. And then lastly, we have oxygen, so 48 over 84 times 100%. And this is 57.14% oxygen. So that is your answers. And then that'll do it for this worksheet. I will see you in the next worksheet.